Okay, good morning everyone. So today we intend to look at some of the properties of an affine connection using, of course, the notation that is used copiously by Professor Stephen Wembach. We can start from here to show that this, for instance, could be written as that, and also from one of the definitions we could have also for a chronicle delta, this expression being equal to this also implying that equal to that. And so it therefore means that the same affine connector which is equal to this, or defined as this, is equal to that, and that this could also be written as this equal to that. Only that we now have an additional differential of this part and also a change of sign. So starting with the first expression, the affine connection is given by this lambda mu nu equal to the x prime lambda, the here z alpha, the 2 z alpha, the x prime mu, the s prime nu. Okay, there is one thing we could do here. First step, we could say, for instance, this is the same thing as the s rho, the x, the s rho, the z alpha. Now here we have with us the x prime lambda, the x rho, and now this is what we have. Okay, now this is what we intend to do. The major point here, or plan, is to try to take away the primes as far away from these terms as possible. So we want to be able to rewrite this expression in such a way that we'll have such a term or a factor as the x whatever, the z alpha, and then also the 2z alpha with respect to the derivatives, but just without primes under. So the very first step we have taken, we have done that already with the first factor here. You can see that there is no prime here, and we have done that perfectly well by introducing this factor. So we can go further to say that this is the same thing as the x rho, the z alpha, and the x prime lambda, the x rho. Also here, this is the x prime mu, and you can write this as that, alpha, the x prime nu. Okay, this we can further go ahead to write as this, the x rho, the z alpha, the x prime lambda, the x rho, and then next we can say this is the s prime mu, now the x some tau, the x prime nu, then the z alpha, the x not prime, so just the x tau. Okay, so now this is our intention. Now the next thing we can try to do is, well, we can just try to evaluate this factor over here by just expanding it out. Now that is going to give us the x rho, the z alpha, the x prime lambda, the x rho. I open a bracket. For the first term, I differentiate this, treating the other one as a constant, the usual Leibniz rule, the x prime mu, and over there the s prime nu. And this first term or second term here of factor left untouched, the x tau. That is what I get for the first one. Now secondly, I have plus. In this case now, I'm going to be leaving that one, which is the first factor, the x tau, now the x prime mu. Then I'm going to have here the x prime mu again, and then the x tau. Okay, that's about that. Now, of course, as you can see, we are gradually going somewhere. We have this also combined here. We are doing our best, as we are saying, to take away the primes from every such x derivative or partial differential associated with the z's. Well, except of course that we have here with us some ds prime mu. So we are going to try to keep that far away again. So this is the same as the x rho, the z alpha, the s prime lambda, the x rho, and what we get here is the 2x tau, the x prime mu, the s prime nu, and then I have here alpha, the x tau, I have here the x tau, the x prime nu. Now, one other thing I could try to do, well, because of the guess of trying here to guess what it may look like, I can decide to say that this is the same thing as the sigma, the x prime mu, and then this becomes d, the x sigma, and then that alpha, the x tau. Please know that it's perfectly okay to choose whatever indices you want, especially for the dummy indices. I could have chosen whatever index I wanted here. Alpha, beta, okay, well, I already have alpha. I could use delta, gamma, and so on and so forth, so long as it's a dummy index. My only reason for strictly sticking to some of these indices is to be close as much as possible to the answer to avoid any confusion. I'm just trying my best to make sure that in the end, you are able to identify the result I get with what we have written over here. Now, I think we are getting somewhere. Okay, so let's just take one more step before we take some. I can just perfectly multiply through with this. I can say this, for instance, is the same thing as the x tau. Okay, so this is now the s prime nu. Next, I have here with me the x prime lambda, the x rho, and then I have here with me the x rho, the z here, alpha, and then the z alpha, the x tau, and then of course coming over here is going to be plus. This is going to be the x. Let me take that to be the s prime lambda. I have here with me the x rho. Multiplying, it goes ahead here with the x tau, the x prime nu. I have also the x sigma, the x prime nu. And then also coming along, we have the x rho, the x z alpha. This factor, of course, becomes the 2 z alpha, the x sigma, the x tau. That's what you get. Okay. Well, at this point in time, you can see that these two cancel. Of course, what is left of these two terms is some conical delta, rho, tau. So in order to make that a little more elegant, so I can simply say that this is the same, for instance, as the 2x tau, and what I have below there is the x prime mu, the x prime nu, I guess. Yeah, so, and the next thing over there is the x prime lambda, the x rho, and then I have the conical delta that I've stated over here. This cancels with that, and I'm left with the x rho, the x tau. This inevitably had to contract, because if they don't, I mean, we couldn't have made this cancellation. So this is going to be rho tau. Very important to get that correct. Now the next thing I'm going to be left with, we'll be saying this is plus. Again, I'm going to look around there to see if there's anything that cancels. Now you can see that this goes with that. Oh no, yes, that is true, but then no more contractions of any sort. No, that can't happen, please. Sorry, remember one of the main reasons for which we did all this was, that was a very serious mistake. So this is, first of all, the x rho, and then this is going to be the x rho, the z alpha. Now, one of the main reasons why we did this, please, that was not supposed to happen, was if you look closely enough, we have a dummy index here, alpha, alpha, we have rho on top here, we have here with us sigma tau. Now, it just looks like one of the definitions we have for the affine connector here, which is this being equal to that. You can see also alpha, alpha repeated a dummy index, lambda, which is the position here, mu, nu, which is the position here. And now the same thing here. So I have alpha, alpha, but then rho, tau, sigma. Of course, the only thing again there is that is not prime. So this particular factor here is the same thing as this. And then this I have here to be sigma tau or tau sigma, it doesn't matter, it's still the same. So please, that cancellation I was talking about at first will not happen, because we needed that to be the case in this term. And of course you can see that this is what it should be actually, because by the end of the day I'm going to have this to be plus. What I have there then would be the x prime lambda, the x rho, and then the next thing over there is the x tau, and the x here with me prime nu. And so I'm supposed to have next again the x sigma, the x prime mu. That is what I should have over there. And then I have the affine connector, define rho sigma tau. Of course, in this case here, I'm going to have a repetition, so it means if rho is not equal to tau, this whole expression, or no, sorry, this whole term is 0. So in other words, these two have to be said to be the same. And then just rewriting it like we had before. So this is going to be the 2x tau. This is the prime mu, the s prime nu. And over here, like we said, we are going to have to change. So this is going to be the s prime. I'm guessing this term that I have over here should be lambda. So it's looking confusing here. The s prime lambda, the x tau. So remember, we could have changed the whole of this to be either taus or rhos. It wouldn't matter, this or it's all the same. So the next thing that we have will be plus the s prime lambda, the x rho, the x tau, the s prime nu, the x sigma, the s prime mu, gamma rho sigma tau. So as you can see now, let's make our comparisons. This term, for instance, is exactly the same with this. You can see we have a dummy index over here with the x2x tau. This is tau tau, just like I have a rho rho. So I could have changed these taus to rhos. That is allowed for dummy indices. I have the s prime mu, the s prime nu. So the s prime mu, the s prime nu, these are not repeated, so they are the same. I have the s prime lambda, and that is what I've got here. So that is the second term. The first term that we have over here, you can see the s prime lambda, you can see tau and sigma. Below them you have the s prime nu, the s prime mu. Of course, even though at this point you can see that the x tau is over the x, what is it called? The s prime mu, right? Whereas here the x tau is over the x prime nu, and then the x sigma here is over the s prime nu, and the s sigma here is over the s prime mu. In other words, it's interchanged. But however, you can perform this operation of saying interchange every sigma or every tau to sigma. Remember, they are all dummy indices because they both occur here at the Christoffel symbol, or what you call the affine connector. In other words, what this whole term, this whole factor here could be written as this: sigma, the x prime nu, then the x tau, the s prime mu, gamma rho, and then I'm going to have it to be tau sigma. So this is still the same thing with that. So it's important to take note of this, so there was no mistake or anything at all that is looking so strange. So the important thing is to know that these two are dummy indices. We could make that interchange, and so you can understand that we have, in a manner of speaking, shown that this affine connector is indeed equal to that. Okay, I'm moving on to the second expression that we intend to prove here. So let me start with that here immediately. Okay, now this second expression we intend to prove says the x prime lambda, the x rho, the x rho, the x prime nu equal to that lambda nu. Now looking at this very harmless expression, of course it's harmless. Differentiating both sides, for instance, with respect to, okay, looking at the expression that I have already, let me say with respect to x prime mu. I want to differentiate both sides with that. The x rho, the s prime nu, and then of course the right hand side again This over here is just conical delta, and this is just some constant. So that's why on the right hand side we have that expression to give us 0, because it's just a conical delta. And when this is not equal to that, whatever it will be equal to will have to be a constant, and that's it. In fact, it's just equal to 1. Okay, now, so very quickly, let's just go again. We go ahead by saying that this is the x prime mu, and the s prime lambda here, the x rho, and then I have here with me the x rho, the x prime mu. Again, so the next thing will be plus here, the s prime lambda, the x rho, and I have here the s prime mu, and I have the x rho, the s prime mu. I'm guessing that we have all this correct. So just by the usual Leibniz rule, treat this first as a variable, keep this a constant plus. You keep the first a constant, differentiate the second. That's just what we've done, still equal to 0. Now again, we have a plan here as to what we would want to do. And that plan is, first of all, we have this combination, one with primes on top and then prime down. We wouldn't want to have a mixed prime either on top and down. We just want to have the primes on top somewhere or down somewhere. So for instance, this particular term we wouldn't touch. We will simply just merge these two. In other words, this will simply be plus the x prime lambda, the x rho, the 2x rho, the x prime mu, the x prime mu equal to 0. Yeah, well, what we're talking about is we have the prime on top in this factor, but none down. We have primes down here, none on top. So we're going to leave it like that. But here we kind of have them mixed. So we want to find a way again for each of the factors to see how to make a separation. In this case, I would like to do something like this. The x tau, the x prime mu, the x tau of this whole expression, the x prime lambda, the x rho. Of course, still multiplying this, sorry, I need to make that a little bit so because of that. So I'm going to have the x so the x tau, like I said, the s prime mu, the x tau here, multiplying the s prime lambda, the x rho, and then still tagging along is the x rho, the s prime mu. So we're going to have that. And so the whole thing there gives us entirely the x tau, the x prime mu. I bring this forward, the x rho, the x prime mu. Then the next thing I'm going to have is the 2s prime mu, s prime lambda, the x tau, the x rho. And this is going to be plus the x prime lambda, the x rho, the 2x rho, the x prime mu, the s prime mu, and this is equal to 0. So I'm just thinking, now looking at this again, so according to what we said here before, so at this particular factor has the prime just on top, and this has down, this also has down. So you can see that by the time I make one subject of the formula, that's if I make this subject of the formula, I have just something of the nature here. So like I've said, I've insisted in maintaining the set of indices that will eventually lead me to the same result as I have here on the board. But I'm doing this just so that everything will appear a little bit elegant. But again, like I've said before, you are free to choose any other index here and you still end up with the same result. Making this subject of the formula, for instance, it turns out we chose the same rho, so we have rho here, prime lambda, prime mu, prime nu, prime nu, prime. So this entirely is equal to minus. So you can see the big difference here is instead of using sigma, I chose tau. So tau here is repeated for this. Again, lambda is there, and then mu and nu are both here. So in essence, we have by this last expression shown that. Okay, so having done this, the next and very last step, which is just a very simple thing that we'll have to do, is to show the last one. And I guess that wouldn't take so much. So just looking at what we have obtained so far, we have been able to show that that this second expression is true. So in order to obtain the last expression over there, we simply make use of the two expressions we already obtained. So looking just at this first expression, we have written more succinctly, or should I say succinctly, written as that, equal to the x prime dot, the x rho, the x tau, the s prime mu, the x sigma, the s prime mu, and what we've got here is some gamma rho tau sigma plus the s prime lambda, the x rho, the 2x rho, the s prime mu, the s prime mu. So very perfect. This is all, you can see it was all selected. Dummy indices intentionally chosen so that all for the sake of convenience, this just gives us what we want. So you can see in this case, as a matter of fact, that this second expression has already been found. And all we'll have to do is to substitute for this, in this expression, this particular term here. Where is it? Actually, that is it. And we have what we're looking for. In other words, there will be no need being redundant. So this is what we had. We had this before, or this originally. You can see that if I replace this term with what I have here, so that this taking place of this, then this expression becomes this last one that we intend to show. I think that is proof enough, at least for this particular last expression. Okay, moving forward, we shall see how very important these three relationships that we have obtained will be.